All right, well, let's see. So before we start talking about force and pressure, I went back to the partial chain page, and down at the bottom, I put in the two solutions so that you could see that you get the same answer. Recall that the idea here is that we've got a cable hanging and we're just going to lift it halfway up. We're going to winch it up halfway. And so the reality method was this, where we winch it up and the beige links are the ones that go up onto the winch and the black links are the ones that end up hanging. And I said you could treat it just like the beige links with a block that has same mass as the black links and just treat it like the block problem, which is what I did here. And then the initial versus final state or terminal state, you imagine the beige links just staying where they are, and it's the bottom 20 links that get teleported up to the top, which is that setup there. So here is the reality method where we're dealing with work, so you use ADD volume if you're dealing with a three-dimensional density problem, and you use ADD length if you're dealing with a one-dimensional density problem, which is what we're dealing with here. And so this is just acceleration. The density I said was a kilogram per meter. And then length in both cases is 40 minus y, because regardless, here you're imagining your links, your y value is up here somewhere in the beige. That's your random y. Down here where you imagine the teleporting thing, your y is down here. So here your y's are between 0 and 20. Those are the ones that are going to get lifted up to here, so we go 0 to 20. The ones that are going to get coiled up here are 20 to 40, so we integrate 20 to 40. But the distance in both cases, because the cable is 40 meters long, the distance that each of those y's travel is still 40 minus y. They're the same distance, 40 minus y. So in both cases, we have a 40 minus y, and then the dy. And then for the reality case, then we add up all the chain links that are not going to be coiled up, 20 kilograms, mgh, 20 kilograms multiplied by gravity, multiplied by the distance traveled by the block, which is 20. Do the integration, and in both cases you get 5880 joules. So it doesn't matter which way you use.
And the third D in ADD was distance?
Distance. In this context, we would typically say distance. In the section we're looking at now with pressure, the part of the section that we're looking at, often we think of it as depth. If you have a wall that's got water pushing on it, and you look at a strip across the wall, you can still think of it as distance from the top or depth. So depth or distance. So I added that in so you could look at that. And then so trough, of course, with the semicircle is the hardest. Cone and cylinder are much easier. And now we're going to this force on a wall. So hydrostatic pressure. Again, that's what I described already. And we've got a couple of formula things here. The main one that we use is force is pressure times area. Pressure times area. If you divide it by area, you would have pressure as force per unit area, which is maybe more intuitive. Force per unit area is pressure. Pressure is ADD, acceleration density distance, or acceleration density depth. That's pressure, ADD, pressure. So let's take a look at this. So we'll do an example here. So we've got, good afternoon. So we've got our wall, our dam wall, and we have a formula. Notice that our formula lost 2 dimensions. It went from ADD volume to ADD, lost 1 dimension, sorry, 1 dimension. Went from ADD volume to ADD area. So one dimension is gone. When we had the volume, we were finding the volume of a slice, which is a cross-section with thickness, the dy, added thickness. Here, area does not mean the area of the trapezoid that we're looking at. It means the area of this strip. So the area of that strip is the width of the strip times the thickness of the strip. The thickness of the strip is going to end up being dy. So when we think of this, the units inside here, ADD area, those are going to give us units of force. This is going to be pressure multiplied by area, and that's going to give us, that will give us units of force. So I've got all the units on the prior page. You can look at them, and here. You can look at them carefully and make sure they all line up. They will. So let's go ahead and do our example, first example. So there's the formula as they write it, which you can memorize it as it is. I think it's easier to remember a general acronym type formula. I feel like that's a little bit easier. But everything in that formula is going to line up here. So we've got the rho, which represents gravity. That represents acceleration. No, I said that wrong. Rho represents density. G represents acceleration or gravity. So the way they've written it is not in the same order, but all the same things are there. So this piece right over here, this is area. The width of the strip multiplied by the thickness is area. That'll be the area of a rectangle. So that part there is area. Okay, so let's try one of these. So trapezoid. A trapezoid, when you're dealing with one of these force problems, is a heck of a lot easier than the trapezoid that we were dealing with. Like that trapezoidal trough was a little bit hectic. It's a lot easier when we're dealing with pressure and force. So it's not going to be as bad as those were. So generic formula, force is ADD area. And we're going to draw a coordinate system here. So usually I like drawing the coordinate system kind of in this position. And what we're going to do is take a representative element, which is going to be horizontal. So this is a representative element at a random y. So think of that as a very narrow rectangle. And when we get to this area part, that is what we're talking about, the area of that red element. So not the area of the trapezoid. It's just a tiny, thin little rectangle. So the area is going to be W times dy. W is going to go all the way across from the left to the right. Question?
So we did the semicircular troughs. Will we learn how to do the trapezoidal troughs, or will it be similar to this? Will it be like a mix of the two?
I think we did trapezoid trough too, didn't we?
No, that was us like an hour ago.
Oh. So the trough, we did not do a trough. Oh, yeah. The trapezoidal trough, actually, with water in it, the 3D trough, is way easier than the semicircular trough. So what you just said is true. The trapezoidal face that we're dealing with here will be identical to what we would do if we were doing the 3D case. So if we were doing the 3D water trough case, it would be the same. You still need, so if you imagine this as a 3D trough, you still need the width of that. Your cross sections will be rectangles, your horizontal cross sections. So you still will have to do the crux of what we're going to do here, which is find W, the length all the way across. So yeah, they will be similar, but easier than the semicircular trough. Okay, so let's go ahead and fill in what we know so far. So we are going to integrate acceleration, so that's A, so that's acceleration. The density here, we're dealing with water, so we're dealing with 1,000. So ADD, acceleration density. And again, you can think of this as depth or distance from the top. So we're looking for this distance right here. This is the second D. And what would that be?
20 minus y?
Nope.
15 minus.
Yeah. Everyone agree? So 15 is the height of that wall, so 15 minus y, that's going to be the distance below the surface, or the depth. So there's the ADD, very similar to what we did with our 3D density things. With our pumping problems. Now we get to area. So area, again, is the area of that little tiny rectangle. It's just going to be width times dy, that's area. Width times dy. So in order to find that width, we are going to need to find the equation of this line over here. Let's see, what color? Let's go purple. So this line right here, if we can find the equation of that line and then isolate x, that would measure across here, right? If we can find the equation of that purple diagonal line and then isolate x, that's going to measure half the width. Okay, so let's find that. Well, to find the equation of a line, it's probably easiest if you just think about 2 points on the line. This point right down here, I'm going to refer to as 5, 0. And then this point up there, let's see. What do you think that point's going to be? 10, 15. Perfect. So that's a pretty straightforward way to get to the equation of this line. So the equation of this line is going to be y minus, you can pick either of the 2 points using point slope formula. Picking the point with a 0 is the easiest, so y minus 0 equals slope. So that's rise over run. So we're going up 15, so that's the rise, and we're going over 5, that's the run, so 3 is the slope, times x minus 5. So the equation of this line is y equals 3x minus 15. And again, if we isolate the x, we're going to turn this line into a line that's focused on y values into a line that's focused on x values. So we're going to isolate the x. We'll have 3x equals y plus 15. We'll divide it by 3. So we'll get x equals 1/3 y plus 5. So that right here, this is w over 2. So that's going to equal w over 2. So, that said, what does w equal? W is going to be 2 times x. W is going to be twice that x value that we isolated right here. So, if we double it, we're going to get 2/3 y plus 10. So that is the width across the trough, which will be the same way that you find the W to find your cross-sectional area with the volume problems. Austin?
Is it possible that you could also get the width by subtracting the right line minus the left line?
Yep, absolutely. If you've come up with the x expression for this, the x expression for that, you can do right x minus left x and get it all in one fell swoop. It's just that you're finding one extra equation of a line. So it's a little more, tiny bit more work. A skosh more work. So over here, area, we have 2/3 y plus 10 multiplied by dy. So that is going to be the area. D, the second D, that's that one. All right, any questions up to that point? So how about limits of integration then? 0 to 15. So we're going to start at the bottom of the wall and go up to the top of the wall. So 0 to 15. We're thinking about every strip, all these horizontal strips that are stacked on top of each other from 0 to 15. So we're going to add up the force on each strip. On each strip, the force is essentially constant. So we'll factor out the 9,800. the integral from 0 to 15. This is a little bit messy. We're going to have to FOIL. So distribute the 15 across, distribute, you know how to FOIL. So that's going to be 10y plus 150 if I distribute the 15 across. And then I'll distribute the y across. That should be a negative. So that should be our foiling. Okay, so then it's just a matter of integrating and plugging in our limits. So we've got 9,800 multiplied by 5y squared plus, oh, I guess I could have done some cancellation, right? Don't those y's cancel out? Whoops. We have a 10y there. Wow, humbug. We have 10y there and a minus 10y there, so those cancel. So when we integrate, we're going to have 150 times y minus 2/9 y cubed from 0 to 15. Plugging in 0 doesn't count. We only worry about the 15, so we'll have 9,800. We'll have 15 times 150, so that's 225 with a 0. Minus 15 cubed times 2/9. Whatever 15 cubed is, that's too big for my brain. And then we add that all up and we get our answer. And what will the units be here for the force on this wall? Say again? Newtons for force, right? Newton meters is work, and we took away one dimension. Took away one dimension of length, so we went from volume to area, which means we're going to go from Newton meters to just newtons. So this will be force in newtons. Whatever that number is. All right, questions on any of the pieces to the puzzle here? All right, so let's try another wall. We'll do one that's like a triangle, upside down triangle. So we're in a similar situation. We've got water pressing against this triangular wall. We know that our formula is going to be ADD area. So that's where we'll start. So the force will be the integral of ADD area. And 9.8, that's the acceleration. And we're dealing with, they have to tell us somewhere what's pressing on it. Doesn't look like I told you here on the test. It will definitely tell you what it is. It's water. So water is going to have a density of 1,000. And then how about depth? So there's our element at a random y. The full distance is 30. The partial distance is?
30 minus y.
Yeah, 30 minus y. So it's going to be 30 minus y for the depth, or distance below the surface. And then area. Okay, so area, once again, we don't mean the area of the triangle. We mean the area of this very little thin rectangle right across there. That's what we're trying to find, the area of that rectangle. Let's take that off. We don't need two colors on there. So we want the area of that rectangle. The height of that rectangle is just dy. So all we have to do is figure out what w is. And then we're golden. So once again, we'll put a coordinate system here. and we'll find the equation of that right-hand line, which is pretty easy to do because this one goes right through the origin. And we know that a line through the origin has equation y equals mx. So let's see, I think I can squeeze it in over here. So y equals mx. Rise is, how much is the rise? 30, and the run is 10. So we're going to have 30 over 10, so the slope is 3x. Slope is 3. Solve for x. X will be y divided by 3. So that's x. X is measuring the distance just halfway across. So that's x right there, halfway across. So w is twice that. So w is going to be, let me write it over here. W is equal to 2x, which will be 2y divided by 3. So 2y over 3, that's w, and then dy. So this whole piece here, this is area. That's area. So again, it's not area of the triangle, it's area of just the rectangle, and our limits of integration are going to go from 0 to 30. So we'll factor out that 9,800 like we seem to have to do a lot. We're going to factor out this 2/3. We're going to be left with the integral from 0 to 30 of, looks like 30y minus y squared. That makes sense? We'll cancel in a minute because maybe we have some stuff coming from this integral that will make things easier. We'll have 15y squared minus a third y cubed. 0 to 30. And once again, we'll just have to do the arithmetic down here to get that final answer. Let's just see. So plugging in 0 doesn't count. Plugging in 30, we're going to have 15 times 30 squared minus 1/3 multiplied by 30 cubed. So whatever that all adds up to. I can add it up after class. What are the units? Just newtons. Yeah. Yeah, if somebody got a number, tell me what that number is. If you should get some fraction. Oh, actually, it's not a fraction. I don't think. No, it's not a fraction. All right, so any question on any of the steps? ADD volume, ADD area, ADD length. So we had 3 different iterations of that formula.
What's the unit for length?
Meters. So meters for length, kilograms for mass, newtons for force, Newton meters for work. Density would be kilograms per square meter here, along there. Yep.
29,400,000.
I'm gonna need a little more space. 29,400,000.
Yep.
If we
we have value like that in the test, can we express any scientific notation?
Yes. Totally fine. If you want to use scientific notation, it's legit.
2.94 times 10 to the 7th. Or 2.947, however you write it.
All right, so any piece of that? Question?
On the test, do you want it in that notation or do you want it in science?
Either one's fine. Totally fine. Totally fine. All right, let's do. All right, as soon as we see a circle, we panic a little because we've already seen that with circles, you deal with semicircles, which means solving for the right half, solving for the left half, blah, blah, blah. It's a pain. But we are just going to set this one up. And if you are one of the integration elite, you can try to do the integral. It can be done by hand, pretty, not easily, but pretty readily. And that's the answer you should get if you want to do it. Okay, so we've got a pool 4 meters deep. It's filled with water. There's a viewing window, radius of a half, tangent to the bottom of the pool. We want to find the force on that little window. So I always set these up based on reality. I draw the coordinate system here so that the x-axis is matching with the bottom of the pool. Some people will set it up so that the coordinate system goes right through the center of the circle. That makes finding the center of the circle, that makes finding the equation of the circle maybe easier, but that's still, then you have some extra work you have to do in terms of finding other coordinates and things, other limits of integration. I find it easiest just to have your coordinate system model the physical situation. So there it is. We are going to need the equation for this circle here. This is a circle centered at 0, 1/2. So the equation of the circle is x minus 0, quantity squared, plus y minus 1/2, quantity squared. So with center 0, 1/2. That's the equation of the circle. And then the right-hand side is just the radius squared. So that will be the equation of the circle. So once again, we need to find the equation of the halves, the right half and the left half, or maybe just the right half and double. That symmetry will work. So when I isolate x here, subtract off the y's, take the positive square root, that's going to measure and find this distance from here over to here. That little red segment, right? That's going to find half of that blue. The whole blue we're thinking of as width. And then that little red piece right there, that's going to be the x right there. So that is the right half of the circle. All right. So let's go ahead, and I put some of it down there, but we'll just do it right here. So force will be the integral from where to where, do you think?
0 to 4.
So we're looking at just the force on this little window. So 0 to 1. That diameter of the circle is 1. So we're going to have force at each of these cross-sectional strips from 0 up to 1. So does that make sense? So 0 to 1. And then we have ADD. ADD is acceleration, density, and depth. What's the depth going to be there?
1 minus 1.
So we're going to be there to there. We want to know how far down is this element. So 4 minus y, is that what you said? Yeah. That's what I heard. 4 minus y. 4 minus y, that's the depth of our element. is everybody following that idea that if the whole thing is 4 and this thing is y, then that thing's 4 minus y? Is that all making sense? Okay, so now we have ADD. We need ADD area. So area is going to be the width of the strip. That's all the way across. That's the blue. The red is just half of it, though, right? That's just measuring from the y-axis over to the circle, so we have to double that. So we're going to double that x value right there. So we're going to have 2 square root. And this one we're not simplifying. We're just going to leave it as a nice big old honking mess. But if you want to integrate it and try to resolve the integral, you may. So there is our setup. So this one, just the setup. So we won't go any further on that.
So I'm assuming on the exam we won't have anything as gross as this?
Not that you have to run all the way through.
Oh, that way it's run through.
Yeah. Setup, definitely possible. But integrating this turns into a total mess. We had one that was kind of a difficult integral last time where so the way to go, we'd have to let u be what's under here. But its derivative is not going to match that, which is why it's a little bit harder.
Can you scroll up?
Yeah. Question?
Would you like to do integration by parts or something?
No, you don't need it. You can do integration with just regular substitution here. It will work. It's just there's a little trick that if you start working on it and you post it into the question area, I will point you in the right direction if you want to try to figure it out. It's a really clever integration. It's just substitution. It's just clever. The key is that you're going to have to break this 4 apart into a sum. All right, so we had one question that we didn't finish back here in there, 6.6, number 7, page 7. We didn't do this one, so let's go ahead and do that one now. We'll do a little refresher on surface area. So this is a surface area. The application piece is not that complicated. They're just saying find the volume of paint necessary to paint this surface if the paint is 0.0015 meters thick. So we'll do our regular math to find the area of the surface, then we just have to multiply by 0.0015. So they tell us our limits of integration, -8 to 8. So we've got part of a circle, it's being rotated around the x-axis, creating this ring thing. Sideways barrel. And we want surface area. So surface area, remember surface area, the idea, 2 pi r. If you take one point and you rotate it around the axis of rotation, so you rotate it around, you get a circumference. You get a circumference of a circle. That's what the 2 pi r is, circumference. And then that ds is a diagonal little segment so that creates a frustum of a cone, base of a cone. And then we integrate to get the total area. So the frustum of a cone is a mini area. And if we add up all those mini areas, we get the total area. Problem is we don't know limits of integration with respect to s. So we have to convert to x or y. That's done with the Pythagorean theorem. And we've seen it with arc length, what it looks like. We've seen it a bunch. So s will equal 2 pi is going to come out to the front. Limits of integration. We could go 0 to 8 and double it, right? Because there's just as much area to the left of the y-axis as there is to the right. So let's go ahead and use symmetry in here. So I'm going to actually put in a symmetry 2 here. So this 2 is by symmetry. And we'll go 0 to 8 with that doubling. So that red 2 is a symmetry 2. So our integral is just going to be focused on this right half that we're creating. That's a little too far, so we'll go right there. Okay, so 2 pi r. R is the function. So we create the equation, well, we solve for y, right? The equation of the circle is given to us, but we solve for y. So y will be the upper semicircle. So y is going to be the square root of 100 minus x squared. Write it with fractional exponent like that. So there's y. So that's r. So now we've got 2 pi r done. So 2 pi, and then there's the r. All that's the r. So there's 2 pi r. ds, we do the square root of 1 plus the derivative squared. Same thing we've been doing. All right, well, we need the derivative then. So let's come over here and find the derivative before we do any more over there. So we need y prime. Easiest to differentiate right here. Pop the half down. Subtract 1 from the exponent. And then multiply by the derivative of the base. So that's the first derivative using the chain rule. So y prime, let's clean this up a little bit. We're going to get x divided by the square root of 100 minus x. And we know that this whole arc length formula business, we need y prime squared. So y prime squared is going to look like this. Is there any piece of that?
Wouldn't we keep the square from inside the parentheses? Like, I'm just thinking like product rule for our derivative.
So for a derivative, so half comes down.
Right.
Oh, where's that square? That square?
Yeah.
I'm sorry, yeah, that one should be there for sure. Thank you. So that's an x squared there, and that's an x squared there. Thank you. Yeah, great catch. So that's 1/2, subtract 1. All right, I didn't that's not even the derivative. What's the derivative? Negative 2x. Jeez. Terrible math. Terrible math. But I got lucky because the squaring, that negative is going to become positive. Jeez. Okay. Now do we agree that that's the right derivative?
Yes.
All right, I'm going to go through it in my head again. Half down, subtract 1, multiply chain rule. 2's do cancel, minus pops out in the numerator, squared. Okay, I agree. All right, whew. Tough stuff. So square root of 1 plus the derivative squared. So we have x squared divided by 100 minus x squared. And now we've converted from ds to dx. So that whole big old mess right here, all of this, that's ds. Square root of 1 plus the derivative squared times dx. Okay, let's combine this thing right here. Maybe I'm going to rewrite this first thing so that it's also in the form of a root, just because it'll be easier, I think, to think about combining them when they're both written as square roots. So if they're both written as square roots, remember that if you have two roots multiplied together, it creates one bigger root where you multiply the two insides together. So we're going to take the inside of this one, take all that, and we are going to distribute it to each of the terms in the second square root. So we'll do that carefully. We'll end up with 4 times pi on the outside. Well, we still have this monster square root. 100 minus x squared multiplied by 1 is that. Multiplying it by the second fraction, we end up with x squared, positive x squared, ooh la la, which cancels very nicely. The x squareds cancel, the square root of 100 is 10, 10 factors to the front, so we end up with 40 multiplied by pi, 0 to 8, and the only thing that's left is dx. And what's the integral of dx from 0 to 8? 8. The integral of a differential is the length of the interval. 8 times 4 is 32. So we end up with that. And we here are finding a surface area. So, but they gave us, what, meters as our unit? So these should be meters squared. So that's the calculus part of the problem. And then if we want the volume of paint, the volume of paint is just this multiplied by the 0.0015. Whatever that gives us. And this volume will then be meters cubed. So if we multiply those two numbers together, we'll get something that sits in front of the pi.
Where did the decimal 0.015 come from again?
That's the thickness of the paint. So that's given.
Oh, given, up there.
So we have a 1.5 millimeters. We have to convert it to meters, so we move the decimal. Okay, any part of that that you want to ask about? Yeah?
Why do you have to turn dx into dx?
So when we look at this graph here, we know that these numbers are x's. We know that these numbers are y's, but we don't see any s's. Right? There's no s. If for some reason you were in a coordinate system, like a polar coordinate system or something, maybe you could have like a coordinate system that was along the arc. That is where the s's are coming from. They would be tilted along the curve in the xy plane. But that's not how we do things. When we put a curve in the xy plane, we know how to measure y, we know how to measure x, but we don't know how to measure s directly. So what we do is convert that to either dx or dy, one of those two, because we have information about the x's and the y's. So we have to convert to x or y.
What's the volume again?
320 pi times 0.0015. Did anyone type that into your calculator?
I got like one. Oh wait, no, I.
Something else,
Never
yeah.
mind, never mind.
0.48.
Or 12 over 25, whatever.
Yep, 12 over 25 would be the ideal format. Because when you look at 12 over 25, that's not been rounded, but 0.48, you're like, I don't know, was it rounded or not rounded? You don't know, can't tell. Yeah, and if they asked to round to a specific decimal point, you could put the pi in there too. Yeah, right. If the problem says round to 2 decimal places, then multiply that all with the pi and get it rounded.
The majority of the time it asks for exact terms.
Exact numbers. Good to know.
Yeah, usually we like to leave it exact. Usually. All right, let's go to our last section in this unit, which is it's very short, and it's not on the worksheet, as you should know by now. The worksheet is just area and volume. You've got to get good at that area and volume stuff. So the worksheet is just those two components, not any of the stuff in 7.3. So that's due tonight by midnight, the area and volume. And on Tuesday, we'll spend the whole day reviewing for the test. remember that in OneNote, prior exams are right here with the answer keys. So the test that was in the spring, the answer key in the spring, it's all right there. And this 7.3 is on the test a week from today, but we're only going to do the very basics of 7.3, just a cursory introduction to hyperbolic functions.
Out of curiosity, why is most of chapter 7 cut?
Most of it is covered in more specialty type courses. There's even some Calc 2 classes that have moved away from the hyperbolics. Like my son is doing PDEs right now, and they use a ton of hyperbolics and PDEs. So they're just learning hyperbolics and PDEs right now, although he did it in Calc 2, but they don't assume that anymore. Most curriculums will still include basic hyperbolics in Calc 2, but some don't anymore.
Okay.
And they just sort of put them where you need them. So if you never go to PDEs, you may never do hyperbolics unless you had it in Calc 2. But it's an important thing to do in Calc 2. There's a couple of ideas that are super important that are sort of common in the world that are nice to know. So one of the videos for this week is the catenary. And the catenary is the curve, or if you're British, you'll call it a catenary. But a catenary is it's got the word cat in it. You know, it's the hanging cable. It's the relaxed cable. And back in the day, the question was, well, what mathematical object is that hanging cable? Is that relaxed cable? So it's not pulled taut, it's just hanging. And it took a lot of work. That cable looks like it could be a parabola, looks like it could be a vertical hyperbola, but it's not. You cannot find a parabola that maps the catenary. You cannot find a hyperbola that maps the catenary. And the curve that maps the catenary is the hyperbolic cosine, which is why it's so important. So they use the hyperbolic cosine all over the place. You'll turn it upside down to make an arch that can sustain itself. All those kind of things. So it's nice to have a brief introduction because that's such a common type of curve that you run across out in the world, the catenary. And then here are the two hydrostatic ones. I just kind of stacked them up here, week 4 and 5. You should definitely watch those, especially if you're going on in engineering, because this concept of hydrostatic pressure and the paradox will come up in those classes. And the professor that does these two, she does a great job of kind of explaining why things are what they are and does some cool examples. So those are definitely worth watching. And then in the next chapter, we'll get to some of this stuff like Gabriel's horn. Gabriel's horn is one of these objects that has finite volume and infinite surface area. So finite volume, infinite surface area. It's going to be similar to the Koch snowflake. Koch snowflake is a two-dimensional thing that has infinite perimeter but finite area. So those are the...
The Koch snowflake video is still private.
Still?
Yep.
Really?
Yeah.
I fixed it, I thought. Didn't I fix it? Okay. I could have sworn I fixed it.
I saw you shake your head.
Why the heck will it? Whoops.
Here we go. Fun. Do you borrow that? Take a seat.
Clear your cache.
Oh, no, never mind.
I did.
You did? It should be there now.
Yeah, someone.
Was it you that told me originally?
No.
Or was it Daniel? Someone told me originally
I
that
told you
the link
originally,
was
yeah.
not working. Yes, so then I went in and fixed it on day 2.
Do you need a portable charger?
So it should be working now. Should be. Give it a shot again. And if not, just empty your browser cache or try a second browser. Should go. All right, so anyway, there are some good applications with the hyperbolic, but we are just going to do some basic ideas. Let's first talk about the definition of the hyperbolic. So the trig functions are called the circular functions because they come from a circle. Simple enough. The hyperbolic functions are called the hyperbolic functions because they come from a hyperbola. So this is the unit circle which we use to generate the trig functions. This is the unit hyperbola. We use only the right half. That's the unit hyperbola that is used to generate the hyperbolic functions. Now there is one thing that is common to both, and that is that this area right here, if you look at a sector area in a unit circle, that area is t over 2, and the t here is, and it's the same idea. So the area is t over 2, so in other words, t is 2 times this area. And that's the same case with the hyperbolics, that the t value that you see in your hyperbolics will be twice that hyperbolic area. They call it a hyperbolic sector. When we say sector, we usually mean a circular sector. So when you hear the word sector, that's what you normally should be thinking of. This is a hyperbolic sector, but same concept. So that's the one connection. You don't need to know that, it's just interesting. So it sort of draws the connection why we would use basically the same words. Cosine and hyperbolic cosine, sine and hyperbolic sine. So they're very closely related. Now here are the official definitions. And this is what's really interesting, and I think this is also an important part for when we get to infinite series. How many of you have heard of Euler's formula? What is the version of Euler's formula that's the most famous in the world? E to the pi I. So plus 1 equals 0. That's the most famous math equation in the world. It's been the most famous math equation for thousands of years. Look at that equation. Has anyone never seen that equation? A few of you have never seen it? Yeah, a lot of you have never seen it. Can you see why it's the most famous equation in the world? It's got the 5 most important constants in math in one equation with nothing else. Right? There's no extra crap in there. It's e pi I 1 and 0. Right? It's the 5 most important constants that you ever see in math all in one simple equation.
How do you take a number to an imaginary
Stop talking. So we won't talk about that in this class. We won't talk about it. But when we get to infinite series, we will be able to see why that equation is in fact true. So we'll talk a little bit more about what that means when you have the I up in the exponent position. But that's Euler's formula, most important formula around because it's got all the constants, nothing else. So that's kind of cool. And so when we get into, there's a form of a complex number where you write a complex number like this, cosine theta plus I sine theta, if it's on the unit circle, or if it's not on the unit circle, you'll put a radius out in front of it. And it becomes very clear when we do infinite series how these functions are going to be connected. We'll show it. We'll leave it at that for now. When we get to infinite series, we'll show how these things are all connected and how you can have that equation. So the first thing, it's not true with the trig functions. With the trig functions, we say that the definition of sine and cosine, we basically go to the unit circle and say cosine is the first coordinate, sine is the second coordinate. The hyperbolics are a little more elaborate. The hyperbolics are actually defined in terms of the exponential function. And the way we think of cosh, this is usually pronounced cosh, some people will say cosh, does not matter. It's not like the trig functions that are used ubiquitously where we've all come down to sine, cosine, tangent. With the hyperbolics, they are not used ubiquitously, so people pronounce things differently. I will call that cosh and sinh. Some people will say cosh. Some people will say other things. Hyperbolic tangent, tanch. The 3 that people have complete variation for are the next 3. So tanch, cotanch, sech, cosech. That's how most people will say them. Tangent, cotanch, sech, and cosech. But it's definitely not, airtight. Some people will say things slightly differently. But when you look at the hyperbolic cosine, it's the average between exponential growth and exponential decay. And that's what creates the hanging cable. So we've got exponential this way, we've got exponential that way, and they average together into the hanging cable. sinh is the average of the difference of growth and decay. And if we look at the graphs of them, here are we're not going to look at the graphs of the other ones. But the hyperbolic cosine, the catenary, is right there, goes through 0, 1, and it never touches hyperbolic sine, the sinh. So sinh is going to look a lot like the tangent, except that tangent has vertical asymptotes. Sinh has no asymptotes, no vertical asymptotes. It goes out forever to the right, and it asymptotically approaches the hyperbolic cosine all the way out to infinity. So there's a picture of the two. Important points are that hyperbolic sine of 0 is 0, and hyperbolic cosine of 0 is 1. So those are the only 2 points we really care about. And just notice that the hyperbolic cosine is always positive, right? It sits above the x-axis. So it's always above the x-axis. You never have to put an absolute value around hyperbolic cosine because it's always positive. So that's what they look like. You're not going to ask you the graphs or the definitions on the exams. We're going to look purely at derivatives and integrals just so we can get some flow with those. Okay, so that's just all background information. So here's what we are focusing on. And there really is a strong parallel to what you already know. So notice the 3 primaries. In trig, the 3 primaries are sine, cosine, and tangent. In hyperbolic trig, the 3 primaries are sinh, cosh, and tang. And notice that their derivatives parallel what we did with trig. So the only difference is that there's no minus sign, right? In trig, the derivative of cosine is minus sign, but there's no derivatives. Like in trig, all the cos have negatives, right? The derivative of cosine is negative. Derivative of cosecant is negative. Derivative of cotangent is negative. Here it's totally different. Here it's not totally different, but it's different. The 3 primaries all have positives, but it's still lined up like sine and cosine, and derivative of tan is secant squared, derivative of tangent is sec squared. So it parallels very nicely. The big thing we have to remember that is the negatives are all with the non-3 primaries. So the 3 primaries are positive, and the 3 secondaries are the negative ones. But the functions themselves all match parallel to what the functions were with trig.
So the derivative of negative cosh would be negative sin.
Yeah, never negative sinh. Yep. Yep. Sinh. It's a sinh. So there's where the derivatives are. And as you know, every derivative formula corresponds to an integral formula. The hardest thing here is, other than the pronunciation, is remembering that the minuses go with the non-3 primary functions.
So is this something we have to memorize for the exam?
You'll have to know the derivatives and integrals for the exam. Yes.
Okay.
Yeah. Now, in terms of integrals, you do not need to know this integral. You do not need to know this integral, but you will need to know this one and this one. And we'll talk about why they are the way they are in just a second. So the only 2 integrals that are not standard up here are those 2, which we'll show you how to do them in a second.
Do we have to memorize any identities?
For the hyperbolics, no. So none of the hyperbolic identities, which are right here, next page. Oh, no, where were they?
Previous page.
Previous page.
First page. Second page.
That page, yeah. Where it says definitions. There. So, yeah, these you will not have to know. These you won't have to know. But just notice, so up here we talked about cosh and sinh, average of the growth and decay, etc. These all parallel as well. So let's just focus on this is the most important identity for the hyperbolics. instead of sine squared plus cosine squared equals 1, you have cos squared minus sinh squared, which is 1. And the one thing that's pretty easy to remember that, oh, there's a negative instead of a plus. But the way that you remember that cosh comes first is that if you think of the graph, cosh is the bigger one. It's above the x-axis. It's higher than the sinh. So if you're going to end up with a positive 1, you've got to do the order cosh squared minus sinh squared, because cosh is bigger in magnitude. So there's still 3 Pythagorean-ish identities. Sum and difference identities look very similar. The power reduction looks similar, except that the numerators are just flipped. With sine squared, it's 1 minus cosine of 2x instead of cosh 2x minus 1. But they're parallel all the way through. So if you need one of these identities on the test, I would give it to you. So you don't need to know any hyperbolic identities, only derivatives and integrals. That's it. And of the derivatives and integrals, it's all these basic derivatives and integrals, and then any other integral we do with substitution. Okay, so we'll do some examples of that now. So let's do derivatives first. So the 2 basic derivatives, just like in when you first learned the derivatives of sine and cosine, you use those 2 derivatives to find all the other derivatives. We're going to do the same thing here. So our starting point is that we know derivative of cosh is sinh and derivative of sinh is cosh. And we're going to start from there and then go on. But I just realized it's actually 3 o'clock. So let's go on a break. Yeah, let's do that. Let's go on a break. Ari, question?
Can we go back to that?
Yes. All will be revealed. Okay, so there are our basic derivatives and integrals. Let's try them. So the first thing is that the derivatives of the primary 3, sinh, cosh, and tant, are all positive. The other 3 are all negative, so just have that in your mind. And then here we're going to start with our basic 2, sinh and cosh, derivative to each other. And then we want to prove, that's what they want us to do in these 2, is prove that the derivative of sech is minus sech tant. So that's what they want us to do, is to prove that. So here's what we're going to do. So the derivative of sech, which we can just use the prime notation, is the derivative of, so we'll rewrite sech in terms of cosh and or sinh, and we know that sech is 1 over cosh, just like secant is 1 over cosine. So they all line up as you would expect. And now we use the quotient rule. We know how to use the quotient rule, and we know the derivative of cosh is sinh. So we're going to do low d high. So cosh times 0, right, low d high, minus high d low over low squared. So there we have the quotient rule. And of course, cosh times 0 is 0. So we end up with negative sinh divided by cosh squared. And I'm going to separate cosh squared into cosh times cosh. And then we're almost there. Because in the numerator, we can think of this as minus sinh times 1. And so we can form 2 fractions. We can form the fraction of sinh over cosh, which is tant. And we can form the fraction 1 over cosh, which is sech. That will be the hyperbolic secant. So now we can cut to the chase. We're going to have a minus out in front. And we'll write it in the same order they have here. So we'll have a minus sech times tant. Minus sech tant. All right, so you all tried the second one. Use that same technique where you take your coset and rewrite coset in terms of either sinh or cosh or both, whatever the identity is, and see if you can find its derivative to be what they say it is. Yeah, that's right. He told us he was going to be gone. I can't remember where he said he was going. Oh, he's going to a wedding. That's where he is. Ryan's at a wedding. At a wedding. Let me know if you have any trouble rewriting coset. Coset, written in terms of sinh or cosh. Ooh, it's snowing. So just like this one up here, that one up there. So we had to rewrite, and if we just are assuming this information, we only know these two derivatives. We don't know the derivative of that until we rewrite it, then we can use that information. The same idea here, we want to rewrite that coset. If we rewrite coset in terms of sinh or cosh, so how do you write coset in terms of sinh or cosh? Is it 1 over which one? 1 over sinh. 1 over. It is. You can also. It is true that these two things are related also, but we want to relate that in terms of sinh or cosh. So just like cosecant is 1 over sine, coset is 1 over sinh. So, and now we can use the quotient rule. So now we can take the derivative of top and bottom. Yeah.
So I'm understanding from going from here to here.
Yep.
I'm trying to figure out where sec tangent is. Tangent is sine over cosh.
Yep.
And then sec is 1 over cosh.
Yep.
Oh, okay.
That's right.
Oh, okay. I was just confused because it's kind of written back.
Yeah. I said let's write it in the same order there,
Okay.
but that's
Okay.
yeah. 1 over cosh is sec. So yeah, then we're doing our quotient rule. Yeah. So this one should look parallel to the one we just did. We're going to take the derivative of 1 over sinh. So 1 over sinh is how you write coset. Coset is 1 over sinh. And then we use the quotient rule again. So low d high minus high d low over low squared. Whatever your acronym is, some people have different acronyms, but you know the acronym for quotient rule, whatever you use. So here we're going to have low d high, so sinh times 0, minus high d low, derivative of sinh is cosh, all divided by the low squared, so we get sinh squared. So that's going to be our step right after we take all our derivatives and use the quotient rule. And then we'll do a very similar type of thing to what we did before. We're going to write this as cosh over sinh. And then we'll take in the numerator and we'll introduce another constant of 1. So we have that kind of thing. And then cosh over sinh is cotang. 1 over sinh is cosec. So this will be minus cosec cotang. All right, so that's how we can use our two basic derivatives to find the. So if you are in a pinch on an exam and you can't remember the rules that how I laid them out, that the top 3 are always positive, sinh, cosh, and tant are always positive, you can always do this. If you can't remember the derivative of cosec, as long as you know those two, you can get to any of the other derivatives. It's going to be easier in the long run to remember that sinh, cosh, and tant are all positive derivatives, and the other 3 are all negative. But that is one way. Okay, so now, the rest of this section, we're going to be combining these known derivatives, and we're going to mash it together with the chain rule and with other rules that we know, like product rule, quote, whatever, all the other rules. So this says find the derivative here. So f prime of x. So the first thing is that we have to use a power rule. So the power rule says that we have to do what with the exponent? Bring it down and subtract 1. So the first step here will be 1/2 times hyperbolic cotangent, also known as cotange, of 3x, all to the negative 1/2. So 1/2 cotange 3x to the negative. That's the first part. That's the power rule part. Now we have to multiply by the derivative of cotange of 3x.
Negative cosec 3x.
So we're going to have, so negative cosec squared. So negative cosec squared of 3x multiplied by 3. So the derivative of tangent is secant squared. The derivative of tanh is sec squared, so those line up nicely. Derivative of cotangent is minus cosecant squared, and this lines up nicely because it's minus cosec squared. But then we have the chain rule again for this little 3x derivative, which is 3. Yeah?
So we're using chain rule twice.
Yep. Yes, indeed. So let's simplify this then. So we end up with minus 3/2 multiplied by, looks like a cosec squared in the numerator. Cosec of 3x divided by a cotange in the square root. And now it's possible to turn everything back like you do in trig sometimes to sines and cosines, but we're not going to do that here. This is totally fine.
Will we have to on the exam?
No. Nope. Okay, so how about that one? Try that one, 27. Try to find that derivative. Derivative of a log. So you need to know your basic log derivative. And then the chain rule. So basic derivative of a log, 1 over the inside. So we always start, if we differentiate a log, 1 over the inside. And then the derivative of the inside. Before we think about the derivative of the inside, let's notice that it's not one of the primary 3. Sinh, cosh, and tan are the primary 3. Those all have positive derivatives. This is one of the secondary 3, so it has a negative derivative. So we know it's going to be negative. And we see the 2x in there, so we know there's going to be a negative 2 times. So if we have to, we go back to trig. Derivative of secant is sectan. So derivative of sec will be a sectan with the minus sign. So sec tanh. The seches will both cancel. So we're going to have minus 2 tanh 2x. Whew. Question?
Is the x in this case the sec 2x, just without parentheses? Is that
Yeah, they're usually aren't
Oh,
gonna put,
okay.
so it's sec of 2x.
Wait, so it's natural log times sec 2x? No.
It's natural log of sec of 2x.
So double chain rule again?
Yeah, multiple chain rules. When one chain rule is not enough, do it again. Do it again. Yeah, so if we have a double nest, then we're going to have a double chain rule. Double composition. All right, let's remember our product rule. So product rule, we have two functions here. So in your mind, you want to think of this as two separate functions being multiplied together. So the product rule says first derivative second plus derivative first second. So the derivative will be first derivative of second. Again, that's a primary, so its derivative is positive, sinh, cosine, tan to the primary. We know derivative of tangent is secant squared, so derivative of this will be sec squared. So first derivative second plus derivative first times second. Not a lot of simplification there. So now I know that some of you have maybe learned the product rule in a slightly different way, at least with the way you say it. Some people will say first derivative second plus second derivative first, which is fine in Calc 2. It's not fine in Calc 3 though. So you have to use a particular order once your functions become vector functions, which is what will happen in Calc 3. And then you have to do first derivative second, derivative of first second. Because with vectors, vector multiplication is not commutative. So with functions, real valued functions like we're doing, yeah, it doesn't matter if it's 1 times tanh or tanh times 1. Does not matter. But when these become vector functions, it is not true that v dot w and w dot v are the same thing. So not necessarily true. I said dot, I mean cross. If you've done any vectors, you know there's two types of multiplication, cross and dot. And so the cross product is the cross product is not commutative. Yeah.
So then what's the proper version of product rule we should be learning?
First derivative second plus derivative first times second. So when you get to vectors and you're taking the derivative of a product with a cross and not a dot, there's two types of vector multiplication. If you do a cross product, that's how you have to do it. First times second plus derivative first times second. So it's a good habit to get into before you get to vectors. Okay, again, we've got, here's a pretty gnarly one. Let's separate it though so that we see two functions clearly. So we've got the x squared and then we've got the cosh squared. And that 3x is inside the cosh. Now, many people blow this derivative. Let's come off to the side. Many people blow this derivative. If you have cosine, let's go to trig. If you have cosine squared of 3x, and you want to take that derivative, do that on your paper. I want to see how many of you can get that right out of the gate. Take the derivative of cosine squared of 3x. Take that a derivative, and you should get So how many of you got that right? Minus 6 cosine 3x and sine 3x. Few of you? So, yep, you're getting there. You're getting there. So this notation that we use as an abbreviation in trig can be doing us a disservice when we're taking derivatives. For a lot of folks, it's very easy to forget that there's a chain rule thing going on here. And it might be easier if you are one of those people that for whom it's not totally obvious, then you might want to do this kind of thing where you're taking the derivative of the quantity where you take that abbreviated notation and you actually write it out in longhand. So then you see that, oh, we've got a power rule happening. The 2 comes down. We subtract 1, so we get 2 cosine 3x to the 1. But then we have to differentiate cosine of 3x, and we get the negative sine 3x times 3. So it's really easy to blow it when that exponent, where we use this kind of abbreviated notation, when we really mean that thing is on the far outside. That's an outer power. All right, so let's come over here and try to do this one step by step. So the derivative is the first function, that's x squared, multiplied by the derivative of the second function. So that second function has an outer power of a square. So that 2 comes down, it's going to be 2 cosh to the first power of 3x. So that's the power rule part. 2 comes down, subtract 1. Now the chain rule part says, now differentiate the base. The base is cosh of 3x. That derivative is sinh of 3x multiplied by 3. So there is first derivative second. First derivative second plus the derivative of the first multiplied by the second. Little bit of simplification, not a ton. We can write that as 6x squared. Then we have to have a cosh and a sinh of 3x. So you're going to notice that sometimes books will put parentheses around the hyperbolic angle. Sometimes they won't. You just always kind of understand that if there's an x in there, that's part of the angle. There's our... All right, so the only real new stuff here is that we are using hyperbolic trig functions instead of just trig functions. Now let's try integrals. So we've got our basic integrals, and then we have our integrals that have a little twist, a little substitution. So we're going to have to use substitution. So all these integrals are going to involve some sort of substitution. And when we look here, you should be seeing two functions, right? We see that there's a sech and a tanh, and yeah, the sech is squared. But we are essentially dealing with two functions multiplied together. There are three choices for your substitution. You could let u equal sech. You could let u equal sech squared. You could let u equal tanh. Those are the three kind of normal things to do. What you say to yourself always is, in an ideal situation, whatever you pick for your u, its derivative is in the integrand. So when I see that, I look and say, oh, the derivative of tanh, it's one of the primary three, so its derivative is positive. Derivative of tangent is secant squared. Derivative of tanh is sech squared. It's right there. That's a good target. Now there's also if you were to let u equal just sech, so one sech, the derivative of sech, now that's not a primary 3, right? Sinh, cosh, and tanh are the primary 3. So derivative of sech is negative. It would be negative sech tanh. And there is a sech tanh there, so we could get at it that way also, which is always the case with trig and hyperbolics, is we use often more than one way. The simplest way here, though, is going to be, let's let u be tanh. So if we let u be tanh of x, its derivative is a primary, so it's positive, so we get sech squared of x times dx. So the substitution works out beautifully here, so we end up with the integral of u du. Does everyone see that substitution? If we're going to replace tanh with u, its derivative is sech squared times dx, so that whole second part becomes the du. So then this is just 1/2 u squared plus c. And then we just back substitute. So we'll have 1/2 tanh squared of x plus c. So that'll be our antiderivative, family of antiderivatives.
So we will only have indefinite integrals with hyperbolic functions?
There will be, yeah, for the most, yeah, on the test for sure.
Okay, because I was noticing in the notes that there are no
No definite integrals.
integrals.
Yeah, because we don't know the hyperbolic values well. You'd have to know the values well. The only ones we really know are sinh of 0 is 0 and cosh of 0 is 1. Those are the only two real values that we know.
Is there like an arc of tanh, or like a
Height, so
inverse type?
yes. So any function has an inverse, so we have inverse hyperbolics. So we can have the inverse sinh, the inverse cosh, the inverse tanh, the inverse sech, the inverse cosech, the inverse cotangent. Yeah. We will not even think, we won't even think about them though. But yeah. When you're thinking about inverses, the easiest way to think about it is just to replace the x with the y and the y with the x. And graphically it reflects it around y equals x. So anytime you have a function, you reflect it around y equals x, there's its inverse. And you call it blah blah with a -1. But we're not going to deal with those.
Okay, I was just about to ask if the inverse hyperbolics have any like notable uses.
I have barely even seen them. It's very rare that they come up. Yeah. Very, very rare. Okay, this one. Can anyone see the answer immediately? This one is a one-stepper if you are thinking correctly.
Take
1 plus cosh is u. And what's the derivative of 1 plus cosh? Sinh. So let's go to the natural log for a minute, because there's something that is not always carefully pointed out in Calc 1 that we are going to talk about a lot in Calc 2. When you look at this, you all are familiar with writing that pretty instantaneously. But in Calc 1, you don't always talk about the relationship between the numerator and the denominator. Isn't it true that this denominator's derivative is the numerator? Yeah, that's true. If you have this setup where whatever the function is in the denominator, if it's set up so that its derivative is in the numerator, in this class, we're going to call that log form. So it's log form if the denominator's derivative is the numerator. And this is super easy. Let me just write down the answer. The answer is natural log absolute value of f of x. Anytime you have an integral in log form, The answer is immediate. It's natural log of the absolute value of the denominator. All right, why? Well, let's do it. So if we let u equal f of x, doesn't that mean that du is f prime of x dx? All right, du is the derivative of f, which is f prime of x. Well, then this integral, if we do that substitution, we end up with du over u. If we plug in u as f of x, then its derivative is the derivative du is f prime of x dx. That's the numerator. We end up with this. And we just said that's natural log of absolute value of u plus c. And then we just back substitute, so that's natural log absolute value f of x plus c. So this is a form that you are going to see dozens and dozens of times throughout the semester. It is way more efficient to recognize log form than to go through that substitution every single time. So if you recognize that this is in log form, you immediately cut to the chase. It's absolute value, natural log of absolute value denominator. And now we just got through talking about the natural log, the cosh earlier. Cosh is always positive, so you don't actually need those absolute value bars. I would not take credit off if you put them there because it's still true, but you don't need the absolute value bars. So if it's in log form, you're done. It's one step. And if you wanted to write it out, if you don't notice that it's in log form, you're going to do this kind of thing. You're going to say, okay, well, u is either the denominator or an exponent, an angle, blah, blah, blah. So you come through, and you would realize real fast, oh, this integral is going to become that. Mm-hmm.
How do we annotate that we know it's log?
You can just say that it's log form. You know, like a lot of times people will just do this kind of thing and put an LF or something. And just sort of, then you point out that it's in log form. And then this becomes natural log, absolute value of u, and then you back substitute. And then you say to yourself, oh, cosh is always positive, so you don't need the absolute values. You can leave them though, it doesn't matter. But if you just look, that's a lot more work. If you recognize something's in log form, it's lickety split. It's fast. Nice shirt, Austin. So, any question on log form? So it doesn't matter how nasty the functions are. For example, if we have something like the integral, let's pick a function down below, let's say sine squared of 3x. If we take its derivative is 2 sine of 3x, 2 sine of 3x times the derivative of the base, so that's going to be cosine of 3x, multiplied by 3, so I'm going to make this into a 6. So if we do that, now the numerator is the derivative of the denominator, we're done. The antiderivative here is natural log absolute value of the denominator. We don't need absolute value in this case because sine squared is always positive, or at least not negative. So instantaneous. So that's one of those forms that you wanted to sort of have on your radar. Log form. All right. All right, so substitution, again, we need to use substitution. These functions are a little unfamiliar with us, so it might take writing down some things. But we have a few choices here. We see that it's sort of paired off pretty clearly into cotangent squared and cosec squared. And if you think about which one is the other's derivative, which one do you think you might want to choose? Yeah.
Could you break apart the squares and
Yes.
try and get something?
So if we let u be, what do you think the best u would be? Because we know that the derivative, let's look at this one first, the derivative of, so you don't want to use the square as part of the u because then you have chain rule. So if you let u be all of cotangent squared, its derivative is bring down the 2 cotangent to the 1 times the derivative of cotangent, like that's a mess. So we either are going to let u be cotangent or cosec. If we let u be cotangent, its derivative is minus cosec squared. So that's going to be our that's going to be the best way to target this thing. So we're going to let u be cotangent of x. So then du will be, so first off it's negative. And if we have to go back to trig, we do. The derivative of cotangent is minus cosecant squared. So this is minus cosec squared times dx. All right, so there we are. So if we let u be cotangent, don't we start out with a u squared now? Because we have a cotangent squared. So if u is cotangent, we have cotangent squared, then we get u squared. Yep.
But won't it need to be negative u squared?
Right. So when we come up here, so we've taken care of that. Now we're looking at this cosec squared of x times dx, which is right there. So we're going to move that minus sign to the left. So we're going to get a minus du. And that minus sign comes all the way to the front, so we usually would write it like that. And now it's pretty straightforward. So we get negative u cubed divided by 3 plus c, which is minus 1/3 u is cotangent. So minus 1/3 cotangent cubed plus c. Does that seem okay? So with these antiderivative things, at least on this test, they're all going to be substitution. So you want to just try, just look and see what are the individual pieces. And you never, unless it's very, very unusual, would you ever let u be something squared. So you should be looking down into the base of each of those. Cosecant, cosec, cotangent. Look down into the base. All right, let's go ahead and do this one. This one you need an identity for. Let's remember that the identity for sine squared, and again, I'll give this to you if you need it, but if you were doing sine squared, it's 1 minus cosine of 2x over 2. So anytime you integrate sine squared, you have to do that. You have to reduce the power. So the power on the trig here is 2, the power on the trig there is 1. The angle is doubled, but that's fine because that's just reverse chain rule. That's easy. So the power has to be reduced, whether it's sine squared or cosine squared. Tan squared, secant squared, cosecant squared, totally different. It's only sine squared and cosine squared. You have to reduce the power. Similarly, sin squared and cos squared, you have to reduce the power. And so if you needed an identity on the exam, I would give it to you. The identity is almost identical. The only difference is that the numerator gets reversed. So it's going to be cos of 2x minus 1 over 2. So all we do is flip that, and there it is. Now it's just chain rule, and reverse chain rule, I should say, actually. Reverse chain rule. So first off, we're going to factor out the 1/2. So that 1/2 comes to the front. and we are going to integrate each of the numerator terms. So integral of cosh is sinh. But then reverse chain rule, what are we going to do next?
Divide by 2.
Divide by the 2? Because that derivative of 2x is 2, so we have to divide by it. And then what's the integral of 1? It's just an x plus c. So there is our final answer. Now this is a good example of where it does make sense to distribute this 1/2 because you've only factored it out of 2 of the 3 terms there. It's only factored out of this part. It's not factored out of the c. Usually if we write something in factored form, we want it to be the whole quantity. We don't just come in and factor part of it. If you see something like x squared plus x plus 1, you don't ever write it like this. You don't factor, the x out of just 2 of the terms. That's worthless. That doesn't help us. So same idea here. There's no need to have this factored, which is part of it. Part of it factoring is not helpful. So, but you could leave it like that. It's not that it's going to be marked wrong, but. All right, any questions on any of those steps? All right, let's go to the last example here. So we'll use hyperbolics to figure out what the volume of the inside of this inverted catenary kiln is. So 3 minus cosh, that's the curve out in front. We've got it 6 meters deep or whatever, 6 units of length deep. And we want the volume, so obviously we're just trying to find the area underneath the curve, multiply by 6. All right, so there is our catenary curve, creating a beautiful arch. We want to integrate that to find the area, and then we'll multiply by 6. So the area of the face here will be the integral of 3 minus cosh of x. And this is going to go from, we need to know intersection points. We can use symmetry, right? We can either integrate from that left point to the right point, or from 0 to the right point and double it. Obviously, that's kind of the way we've been doing it. So we would have to set 0 equal to the function. So this tells us cosh of x is equal to 3. The only cosh value we know is that when x is 0, cosh is 1. It's the hanging cable going right through 0, 1. So this x value is going to be the inverse, oh, whoops, I said we'd never see it, but we're seeing the inverse cosh right there. We're never going to graph it, but so that value, that x value is inverse cosh of 3. It's an irrational number. We don't know what it is. So our area is going to be 2 for symmetry, and we're going to go from 0 to inverse cosh of 3. Forgot that we get to use an inverse.
Can you scroll up so I can see it?
So we're just solving for x, finding the x-intercepts. All right, so there's our area. We integrate. So the area will be 2 multiplied by 3x. The integral of cosh is sinh. So that's going to be sinh of x. And this will be on the interval 0 to inverse cosh of 3, whatever that number is. Now, one thing we know is that this 0 is not going to contribute anything. We know that sinh is the function that looks a lot like tangent. It goes right through the origin. So sinh of 0 is 0, just like sine of 0 is 0, and tangent of 0 is 0. So that is not going to give us anything. So here is our area. So we're going to end up with 2 multiplied by 3 inverse cosh of 3 minus a composition sinh of inverse cosh of 3. So that is our area. And to get to volume, volume is going to be 6 times this. So it's going to be 12 times this crazy looking expression. And there's no way to evaluate that unless you use some sort of technology. There's no shortcut that's going to allow you to do that. So we will just type it right into Desmos. Desmos does everything so beautifully. So we'll just type that in. So you're going to type it in just the way it looks. So cosh superscript -1 tab 3 minus sinh of cosh inverse superscript tab out 3. And there's our answer. What was that shortcut for the snipping thing? Windows Shift S.
Windows Shift S or Control Shift S?
Windows Shift S?
Yeah.
So Windows Shift S. I need to remember that. That's good to know. Windows Shift S.
You can always look up snip in the Windows box as well.
Oh.
So if you look up snip,
Yep,
this
yep.
will be totally up.
If I do that,
And then when you click
and
on
then
it,
go to, oh, whoops, go where?
You're on, yes, you're in new, so you'll be create new snip. So yeah,
Hit
click on
new, and then you can save whatever.
Yeah, and then,
Oh, yeah. I thought it had the shortcut command there somewhere so that I could see if I forget the command.
mine does on my Windows, I don't know why.
Does it?
popped up on-
But didn't show up. All right. So you get the idea, and then if we were given units, we'd plop in units. But so that is how the inverse hyperbolics might work in practice. All right. Any question on those? So hyperbolics, not hard, but definitely not nothing. So make sure you practice a little before Thursday. So let's go ahead and I'm going to give you some problems to work on. So, oh gosh, that feels so bright. So let's go ahead and I want you to try a, why are you freezing? So we're going to do a volume problem. Question?
What are you reviewing now?
Yeah, we'll go over some problems that that are part of what we did on Tuesday, just to reinforce some of those ideas. So we learned that the hardest trough was the semicircular trough. So let me give you a basic shape first. Let's do a cone. So I'm going to have you find the, let's do an emptying of this cone. Let's suppose that it's filled with water. We're going to say that the radius of this cone up here is 2. And we're going to say that the height of this cone is 10. And we'll go with units that are meters. And we are going to have it filled with water, so empty through the top. when filled with water. So you're going to find W to do that. So find the work done in emptying through the top, just right over the edge, when it's filled with water. And remember that the density of water is 1,000, gravity is 9.8. So how much work? So at this point, you should be able to do all your MyMathLab homework through Chapter 7, all of it for Unit 1. And a lot of you are doing a good job of keeping up on your homework. There's a few of you that are doing less good keeping up with your homework. But at least half of you are almost all the way done.
And by almost all the way done, what do you mean by that?
It's a little big.
Okay, that's not helpful.
Worksheet, though, I can't tell how, I haven't looked at the worksheet. So worksheet's due tonight by midnight. Make sure you get that done by midnight.
Jim, I do have a question.
Yeah. Question on the worksheet?
Would the best way for me to upload everything I've done is to upload an image of myself and snip onto the document?
Yes.
Okay.
Yeah, that's, you don't want to upload photos.
Got it.
You want to, if you take a picture, upload it to your computer, and then you want to do a screen, you want to somehow, it depends. Everyone know how to use the scan feature on your phone so that you're getting a PNG file and not a photo? Right, that works great. Or you can take a photo, upload it to your computer, and then use the snipping tool.
So I can upload this PNG into OneNote?
Yes.
Is it acceptable?
Yeah,
Okay.
totally fine. So if you're going to do the whole thing at once, just insert it right at the end of the thing, and then I'll see it. Yeah, yeah.
Thank you.
Or you can do it at the beginning. Doesn't matter. Beginner, I'll find it. I will find it. Yeah.
Okay, so for the worksheet, since it was all set up but do not evaluate integrals,
Mhm.
right?
Yep.
I typed in the integral to
Yep.
Desmos and then snipped picture the
Perfect.
integral and then put it in the worksheet.
Perfect.
Does that work?
Yep. Yep.
Okay.
Yeah. So Desmos is a great equation editor. If you want to use Desmos and use the built-in math commands in Desmos, that's great. What Austin just suggested. You can type into Desmos and then screenshot it. That's totally fine. Also. Yeah. Whatever works best for you.
Jim, you're kind of in charge of the Math Center stuff, right?
Yes.
I see your email and stuff. When I went by today, this is the first time I saw this.
Oh, the Online Math Center?
Yeah.
Do you all know about the Online Math Center? So if you've perused our OneNote here, down here are the Math Centers. There's Math Center at each campus, including the Online Math Center. So if you click right there, when you're not in draw mode, this will open up the Online Math Center. And so you first have to set up an account. So when you click on that, you just set up an account with your school email address. It takes 2 seconds. And then you can log in. You can't see when there's open slots until you log in. So once you log in, you can see when the open slots are, and then you can make appointments to go to those different times.
Cool.
Yeah.
Thank you.
So that's a super, super good. And then I mentioned a couple times in these questions here, if you come in here, like I check every night. If you have a question, you can snip it right into here, paste it into there, and I'll get back to you. If I don't get back to you within a little while, just send me an email because it doesn't send a notification that there's a new, insert. So you can just send an email to jim.boss@frontrange.edu and say, hey, I just uploaded something to OneNote questions. Can you check it out?
What is the likelihood that you're going to be checking this over the weekend?
100%.
Oh, so because I haven't done much of the homework, if I have a question back in 6.3, I can still.
Totally, absolutely, yeah. Anything in Chapter 6, I'll post it in there.
Okay.
If I don't get back to you in a couple hours, just send me a quick email because I'll get that on my phone, and then I can even do OneNote on my phone easy.
Copy. Okay.
So simple.
Sweet.
Yeah, I check it all weekend.
I just a question with what I've done.
What are we doing? Oh yeah. Oh, let me just get back to that page.
Sorry.
Yeah, I forgot where we were. Let's just get back to here. Yeah. I forgot what class we were in. I thought we were doing pre-calculus. So A, D, D. Yeah, that was great. No, that doesn't look doubled though. Oh, no, because this
Because I
is,
did.
like,
right.
it's not area though. Right, this is, we want to find the cross-sectional area. So it should be in pi, there should be a square.
So far, not bad.
Okay, so let's go through this one. So we're going to pick a general cross-section. This is going to be at a height of y. Cross-section is two-dimensional. We're going to turn it into a slice by adding a little thickness, and that thickness is a dy. So right away we know our integration letter is y. We're going to integrate with respect to y. So we need to find the area of this cross-section here. So area is pi r squared. Okay, well, the radius in general is right there. There's r. Not at the top. At the top it's 2, but down there it's not 2. So we're going to have to set up an equation, build a line. So let's go ahead and build a line in quadrant 1 that will suit us. So here's where we're at in quadrant 1. And to build a line, the easiest thing to do is find 2 points. Okay, one of them's the origin. The other one is, what are the coordinates for that upper point?
2, 10.
2, 10. So 2, 10, and so we know the slope is what?
5.
So why I wrote a 5 in there. 2, 10. I was answering my question as I was rewriting that. So 2, 10, the slope is 5. So the line is y equals 5 times x. But we want a horizontal distance. We need to measure that little purple radius. So we're going to isolate x. So x will be y fifths. There's the radius right there at our random y. Okay, so what is the area of the circle at height y then? Pi times y fifth squared, so y squared over 25. Perfect. Good. So now we have the cross-sectional area of every single disk throughout this cone. And we go to build our volume. We know that volume is the integral of area. So actually, let's pull out the pi over 25. Let's pull that to the front. So pi over 25. So, and let me write the generic formula for a second here. So we're integrating ADD volume. So that's our generic formula, ADD volume for a three-dimensional vessel. A, okay, we know that's 9.8. D, that's the density of water, that's 1,000. And then how about the other D? Depth, which is 10 minus y. So 10 minus y. Right, good. So there's the ADD. Now volume is volume of the slice, not volume of the tank. Volume of the slice, which is pi r squared multiplied by the thickness of the slice, which is dy. So dy is the thickness. Pi r squared is the area. So that is our volume, and we're going to go from 0 to 10. So that is our setup. We'll do one more step on it. So I'm going to factor out the 9,800. That will be in the numerator. And yes, 25 can divide into that. We'll do that in a second. Or at least think about doing it. So then we're going to have 10y squared minus y cubed dy. So that is how it all simplifies down before we do the integration. Question?
What was that worksheet you were talking
The OneNote worksheet?
Yeah,
The one that's due tonight at midnight?
yeah.
And what was your question about it?
What is it?
Is this. So if you go into your private section, I'm just gonna pull yours up, Daniel.
Yeah,
Well, I
you're-
can pull up ours
You can
too.
pull up whatever.
I should be at the bottom.
Yeah, I can't ever remember anyone's last name, so.
Just pull this up too, so it's not on top.
Yeah, I should have done that. Are you at the very bottom already? Oh, literally, okay,
It's till
literally.
midnight tonight, which is 12.
So in your section, under worksheets, right there.
So ask him, is this thing, this is-
So one section on areas and one section on volumes.
Okay, that's due.
And so I mentioned this earlier in the semester. If you write, you can write in here directly if you have a tablet. It's a little finicky though if you have to do any stretching and the words can start moving. So one thing that I often do is I'll do stuff over on the side and then I'll use the snipping tool so that it's an image, copy it and paste it in there and then erase that. Then you don't have any weird stuff happening where the letters are moving around. If you insert it as an image over there, then it captures it, then it just stays as it in line the way you would expect it to. So that's a one thing that you can do that makes it easier. All right, so any questions on our cone then? Yeah, literally at the very bottom, right? Okay. So any questions on that cone? Chapter 7. I'll finish it off while you guys are doing whatever you guys do. All right, so we'll call it quits. Have a good weekend. I'll see you on Tuesday. We'll spend all day reviewing. So do a bunch of math this weekend. Come on Tuesday with questions, and we'll get primed up for exam 1 and get off to a good start. And I'll stick around if anyone wants to hang around and do more math.